everyone, and welcome. Have you ever used a piece of software and just thought, wow, this is so solid and reliable? Well, I'm going to let you in on a secret. It's not magic. Just like a massive skyscraper, the absolute best software is built on a brilliant and often totally invisible architectural blueprint. So today, we're going to pull back the curtain and take a look at that hidden structure. So let's start with this question. What do the world's best apps really have in common with a skyscraper? It all comes down to one word: structure. Both of them depend completely on a well-designed plan that organizes everything into functional, interconnected parts. In a building, you've got rooms, hallways, floors, right? Well, it turns out software works pretty much the same way. These fundamental rooms in our code are what we call sub-programs and blocks. You can think of them as modular components, kind of like prefab sections of a building. Each one is designed to do one specific job and do it well, like calculating a price or rendering a button on the screen. By building with these reusable units, we create software that's organized, way easier to maintain, and a lot less likely to come crashing down just because you need to fix one little thing. Now, of course, every room in a building has stuff in it. Furniture, tools, materials. In our code, that stuff is data. And to be a good software architect, you have to understand two super important rules that govern how this data behaves: its scope and its lifetime. Okay, so this is huge. Let's break this down. Scope is all about visibility. It answers the question, from right here in the code, what variables can I see and use? Lifetime, on the other hand, is about existence. It answers, how long is this piece of data actually going to be stored in the computer's memory? They sound kind of similar, but let me tell you, confusing these two is a classic architectural flaw that leads to these nightmare bugs that are almost impossible to track down. And this brings us to the two main ways programming languages figure out that scope. Most modern languages use what's called static scope. This means visibility is determined just by how the code is physically written. It's right there in the text, like a fixed blueprint. But there's another way: dynamic scope. Here, visibility depends on the exact sequence of function calls that happened while the program was running. It's less like that fixed blueprint and more like an on-the-fly workflow that can change every single time you run the program. So what does all this add up to? Well, it creates what we call a local referencing environment. That's a fancy term, but it's actually a simple idea. It's just the complete set of all the variables and tools that are visible from inside any single room or subprogram. This defines the immediate world that a piece of code works in, making sure it has exactly what it needs and nothing more. And that is absolutely crucial for keeping your code secure and stable. So we have our rooms, and we get how data behaves inside them. Great. Now let's move up to the next level of design. How do we build these code blocks to be not just functional, but really smart, efficient, flexible, and truly powerful? A huge part of that is figuring out how we move our materials, our data, between these rooms. This is called parameter passing, and the method you choose has massive consequences. With pass-by-value, you send a copy of your data. This is super safe because the original is never touched, but it can be slow if you're copying a huge chunk of information. Then there's pass-by-reference. Here, you just send the address of the original data. This is way more efficient, but it's also risky because any changes made in that new room will affect the original data everywhere. And then you have even more complex methods like pass-by-name. At the end of the day, each method is a critical design trade-off between safety, performance, and flexibility. Okay, another big design decision is how we create rooms that can work with different kinds of materials. One way is with overloaded subprograms. This is where you have multiple functions that all share the same name, but are built to handle different types of data. So you might have one add function for numbers and another add function for text. The other approach is generic subprograms. This is like having a single, powerful template that can work with any data type you throw at it. It's really the difference between having a single multi-purpose room you have to reconfigure all the time versus having a master blueprint you can use to build the perfect room for any occasion. All right, now this is where things get really, really cool. What if, instead of just sending data between your rooms, you could send an entire operation? What if you could send a specialized tool or even a robot with its own instructions? That's the mind-bending idea behind passing subprograms as parameters. It lets you build these incredibly dynamic systems where the actual logic a function uses can be swapped out on the fly. Okay, we've got the foundations down. Now let's get into some of the more advanced techniques, the kind of stuff that really separates a good software architect from a great one. So one of these awesome tools is the user-defined overloaded operator. This gives you the power to define what a common symbol, like a plus sign or a multiplication sign, actually means for your own custom data types. It's like you're creating custom-built, intuitive tools just for your project. And the result is that your code becomes incredibly clean and easy to read, which, trust me, means way fewer mistakes. And last but not least, let's talk about coroutines. See, a normal subprogram just runs until it's finished. End of story. But coroutines, they're special. A coroutine can run for a while, and then hit pause or yield and hand over control to another coroutine. Then that second one runs for a bit and yields. And then the first one can be woken up or resumed, and it picks up right where it left off with all its data intact. It's like having these perfectly coordinated work crews on a job site, all working together. This is the architectural pattern that makes so many modern responsive applications possible. So here's the big takeaway from all of this. None of these concepts live on an island. A great software architect understands how all these pieces of the puzzle, the subprograms, the data rules, the design patterns, the advanced techniques, fit together to create one solid, coherent, and stable structure. So let's do a quick recap of the architect's key takeaways. First off, subprograms are the modular building blocks of everything. Next, we saw that scope and lifetime are the two golden rules for data, governing where it can be seen and when it even exists. After that, we saw how parameter passing methods act as the doorways that control how data flows between our blocks. Then we looked at how overloaded and generic functions give us incredible flexibility in our designs. And finally, we touched on advanced tools like coroutines that let us build really complex cooperative logic. Every single one is a critical part of that final blueprint. And that really leaves us with one big final question. We've talked about the blueprints that have built the software we use today, but as our digital world gets exponentially more complex, with things like AI, quantum computing, and globally interconnected systems we can barely even imagine, the real question is, what new architectural blueprints are we going to need to invent for the software of tomorrow?